And hi, welcome back. I just want to pick up where I left off. Okay, so yeah, last time we left off is we want to represent vectors using this coordinate system. Okay. For now we just use 2D first. I mean, most of the time in actual calculations we like to use 3D. So there's SX, SY, and SZ. But for simplicity's sake, let's just start with these two ways first. Okay. Because I mean 3D technically, you will run into more of that in university level physics, and I personally didn't take university level physics. I took engineering, so yeah, let's just start with that. Okay, kinematics 2. Okay, I want to talk about vector addition. Okay, vector addition or vector subtraction. Okay, so remember with this diagram here, going from point A to point B, we travel, the displacement is 3,500 kilometer with this angle theta to the x-axis. Okay, but I said I like to use this SXXY kind of direction, or rather this way of representing, because at least it separates it out into how far you travel in the x direction, and then how far you travel in the y direction. Okay, so that why do you want to do it like that? It makes vector addition easy. Okay, it makes vector addition easy. So let's say you want to travel from AC and then you want to go to you want to travel from A to C, and then you want to travel from C to B. Now, when you talk about vector addition, okay, you add this vector AC to vector CB. Okay, AC to CB. If you add them both together, you get the vector AB. So let me write this down. Okay, AB. In terms of vector addition, this is a very basic vector addition, but I don't know whether they teach you this in O level, but I think A level they may. Okay, vector addition, AB equals to AC plus CB. Okay, so going from point A to point B, basically what this is saying, this math equation here, and these are supposed to be arrows, is going from A to C. Okay, point A to point B is the same as going from point A to point C, and then point C to point B. This is what this equation here is saying. Now, how do we put math into that? Okay, how do we put math into that? So, what's a vector AB? Okay, what's vector AB? Okay, so this displacement here is actually vector AB. Okay, and then what were my so-called, we call these components, yeah? We call this SX and SXY. They are called the x component and y component of the vector. Okay, but you just call this SX and SY. That's the displacement. Okay, 3407.3 and 800. Okay, 3407.3 and 800. Okay, this is in kilometers. Okay, 3407.3 and 800. So okay, this is AB. Now, I want to show that in vector addition, AB equals to AC plus CB. So what's AC? AC is what? Actually quite easy, AC. AC is just going in the x direction, 3,000 kilometer, because I believe that's what I specified just now. AC is 3,000 kilometer. So how do you write this in the vector form? Okay, AC, okay, pardon me, AC equals to 3,000 kilometer in the x direction, 0 kilometer in the y direction. Okay, this is how you write AC. It's not very simple. Now, how do you write vector CB? Vector CB equals to what? So, vector CB, where's the triangle diagram? Always go back to a triangle diagram, very important. Vector CB, okay, again I want to represent how much it goes in the x direction. That's 407.3. So 407.3 in the x direction. 407.3 in the x direction, and going in the y direction, that means going in the y direction just now, which is here. Now going in the y direction, it goes 800 kilometer. 800 kilometer. All right, so that's vector CB. So let me just prove. I'll give you a quick show. I think it's pretty obvious by now. AB equals to AC plus CB. So AC is 3000 plus 407.3 800. Okay, add this together, 3407.3 800 km. Okay, it's very easy to do vector addition like this. Okay, if you have it in this first form, okay, when you have 2306 radians, then you have to separate out. You have to separate out the vectors into the x and y distance traveled, and then you can do this vector addition. So the reason why I really like to use this the reason why I like to use this format of representing vectors, and it's like it's not very nicely drawn, but it's supposed to be like a box, one column, two row matrix, or two row, one column matrix, if you want to use it like that. Okay, of course, the true blue mathematicians and will tell me, or physicists will tell me, there's way more to vectors and all that. But yeah, at a very junior basic level, I guess this is good enough. So, if you want to learn more, you go into more advanced physics, then we talk about it. But we do not really need that. Okay, so for vectors, you want to kind of keep them in this format so that it makes the vector addition and vector subtraction very easy. Okay, so that's all I want to say about this part. Okay, so for vector addition subtraction, you need to do all these trigonometry things, and then you will be able to be fine. Just get used to the sine, cosine, tangent, mostly sine and cosine actually, and you should be fine. Okay, so that is vector addition covered, and I kind of covered the case with cruising altitude. Okay, so that gives you the example of vectors. Okay, so back to our plane problem, right? Our plane problem. Okay, we have the cruising altitude sort of figured out, or at least we talked about some of the kinematics that can go on in cruising altitude. Next thing, let's talk about takeoff and landing, especially on the runway. Okay, let's talk about takeoff and landing. Takeoff and landing. And landing. Because these two are sort of opposites of another. Okay, sort of opposites of another. So I'm going to close the calculator thing and I'm going to increase it here. Right. What's the case in takeoff and landing? Okay, you have a runway. Okay, and your plane is traveling like this. In the takeoff, you start off at the time equals 0 seconds. The velocity or speed. Okay, velocity is 0 meters per second. Okay. Now again, I just mentioned just now, x and y direction. That we tend to want to put this in vector format. So the proper way to do is like this: 0 in the x direction, 0 in the y direction, meters per second. Okay, this is how you do it. Now, if you don't want to write all this, it's better to say like this. If you're talking about runway and we are not even going off into the air yet, you can just simplify our problem to say we talk about vector in the x direction. The vector, the component in the x direction, because we don't even deal with the y coordinate here in the runway. So we just say this: t equals to 0 seconds at time equals 0 where we start. Velocity in the x direction equals 0 meter per second. And then now you don't need to do all these things. That's the proper way. Okay, so at t equals 0, the Vx, we call it, equals to 0 meter per second. And then you want to hit some threshold speed. Okay, you need to hit some threshold speed before you take off, because you need to travel fast enough so that the air can flow around the wings, and then you generate enough what we call lift that can bring your aeroplane up into the sky. Okay, so of course the plane doesn't instantaneously, it doesn't immediately go into this threshold speed. I don't know what is the correct term for it. I'll just call it the threshold speed for now. Okay, so you want to design your runway so that your plane can get up to this threshold speed and then take off. Okay, so your runway has to be long enough. So how do you so-called determine what is long enough for this runway? There are two things you need. At least two things, yeah. Okay, at least two things. So first thing, what is this threshold speed? What is this threshold speed? How fast is this? So for sake of demonstration, I'm just going to give you 100 meters per second. Okay, for different planes, this threshold speed is actually quite different because it depends on the wing design, how heavy your plane is, how much cargo it's carrying, so on and so forth. Maybe there's weather conditions as well that can affect that. So this threshold speed, it may not be a fixed number for every plane. In fact, in different situations, different planes will have different so-called threshold speed. Okay, even the wind direction, the wind that's blowing across the runway, it will affect this threshold speed, because that will affect how much lift you are actually generating with your plane wings. Now, for simplicity's sake, I'm not going to think about all these complicated things. Let's just talk about a still dry day, and then you want to reach 100 meters per second on the plane before it takes off on the runway. Okay, so this is why we need this threshold speed. Okay, so we need this threshold speed. Okay, we need to hit 100 meters per second. That's number one. 100 meters per second. Number two, well, so remember just now our plane's at rest, but we need to accelerate the plane. How much acceleration we have? Can we give the plane? Okay. Okay, so number two, we need to accelerate the plane. Yeah, so we need to accelerate the plane so that it can take off. Okay, how much acceleration? Alright, so I went fast forward, ran for dinner, but yes, now I'm back. Anyway, so we were last talking about how much acceleration the plane can take in this runway problem. Okay, oops. This runway problem where this plane is traveling and it has to reach some threshold speed in order for it to take off. Okay, how much runway do you need? Okay, so this is going to be limited by how much acceleration the plane can take. Okay, this is how much acceleration the plane can take. Now, in terms of acceleration limits, because of course we need to acceleration is the rate of change of velocity with respect to time. Okay, acceleration is rate of change of velocity. Okay, this is acceleration is also a vector. Okay, change of velocity with respect to time. Okay, so this is what acceleration is. Okay, how much acceleration can the plane take? Okay, acceleration limits because we have to speed up the plane until it takes off. Okay, so one thing is the human body. Okay, second is the plane structure. Okay, the wings can only take so much stress, and the fuselage, which is the plane body. This is called the fuselage. It's called fuselage. Okay, this can only take so much stress. Okay, but usually it's the human body that is the problem. I should not say human body is the problem. I apologize. Yeah, human body is the limiting factor. Humans are not the problem. Okay, I don't want to give that label. That's very, yeah. People are important. Yeah. So human body is the main limitation in most of these cases. Okay, why is this the main limitation? Okay, so if you ever rode a plane before, a passenger plane at least for commercial airline, you want to have a comfortable experience. You do not want to be vomiting on the plane because it's going around too fast, is accelerating or decelerating too suddenly. Okay, you don't want any of that kind of thing. So you want to make sure acceleration changes slowly. Okay, and then you don't have too much of it. In fact, I think when you talk about fighter jets, the pilots are supposed to take up to 9 Gs. Okay, up to 9 G of acceleration. What is G? Okay, 9 G of acceleration. Okay, again, you have AI or you have Google. Go and check me out. Not check me out. Fact check me. Acceleration. Yeah, you can see whether this number is correct. What is 9G? G is gravitational acceleration of Earth. Acceleration of Earth. Okay. A lot of times the easiest number to remember is 10.0 meter per second square. Okay, but this is a very rule of thumb number. The closer number is something like 9.80 to 9.81 meter per second square, and this also actually depends on where you are on the Earth, because the Earth is actually spinning. And if you are on the equator, where it's so-called spinning the most, you will actually realize, or rather, it is actually detectable that the Earth is slightly bulged. It's not a perfect sphere, and therefore the gravity at the equator is slightly weaker. Okay, that's one of the reasons. Gravity at the equator is slightly weaker than elsewhere. Let's say at the polar region. Equator is weaker than polar region because of the bulge. Bulge effect. Okay, but this is not so big to change it from 9.8 meter per second square to 8 or something like that. It's more like 0.05, 0.03, that kind of little bit of acceleration. Okay, again, I could be wrong because I'm taking stuff up from memory. My memory could be wrong, but this is if I remember correctly. Again, you have Google, AI, go and search. Yeah, nowadays it's like that, so expect that. Okay, so pilots can take up to 9 Gs of acceleration. So what's 9 G? So 9 times 9.81 or 9 times 10. Okay, 90 meter per second square. Okay, so this is the higher upper limit. You never want your acceleration to go that high, because at this point the person will start to black out, because the blood from the brain will kind of be taken out by this acceleration. So there's not enough blood going to the brain, and then you will black out. Okay, if you don't manage this properly. So this is about the highest you can go, or rather one of the highest you can go. Okay, passenger. Okay, passenger. Maybe I don't use this line. Passenger I don't think you even want to go beyond 2 or 3G. Maybe you want to go 0.2 to 0.5 G max. Okay, even 0.5 is pretty high, because that means that's what? That's like you sitting down like that. It's very uncomfortable. Yeah. Okay. So so imagine if 0.5 G was pulling you in front. Okay, so you are sitting on the plane seat. 0.5 G. That is if you weigh, let's say, 60 kg ish. Okay, your mass is 60 kg. Acceleration is 60 times 9.81. So but the feeling of your body weight is 60 kg. I mean, most of us will use kg rather than newtons, which is the SI unit for force. But let's not deal with that now. Now for yourself, if you have 0.5 G, it will feel like 30 kilogram of weight is just pulling you forward, and that's very uncomfortable. In fact, I don't even think you want to have 10 kilograms. I don't think that's comfortable. Maybe 5 kg. 5 kg is more comfortable, right? So for 5 kg, maybe this is what 0.08 G. Yeah, this is maybe something comfortable for airline. Right? So okay. So yeah, you want 0.08 G. 0.08 G. Yeah, 0.08 G. And maybe that's the max. The max you want to get. Okay? 0.08. So what is 0.08 times 9.81? Oops, 9.81. Okay, 0.7848. Okay, so for passenger comfort, okay, maybe you want 0.7 meter per second square acceleration max. Okay, for airport. Okay, otherwise you'll feel very uncomfortable for sure. So we have maybe upper limit of 0.7 meter per second square. Okay, the other way of writing is 0.7 meter per second square with this -2, and again this is acceleration in the x direction, because acceleration is a vector, so you need to write the xy components, or you use the angle, but I always prefer I like the xy component method. So 0.7 meter per second square. Okay, so how long does your runway need to be? Okay, how long does your runway need to be? Okay, so for this kind of problem, acceleration problem, okay, because the speed is not constant, you cannot just use velocity times time. So what I like to tell people or tell students is use the velocity time graph. Use velocity time graph. And I'll be specific here, I'll use velocity in the x direction. So velocity in the x direction versus time. Okay, always try to write your units as far as possible. And as you can tell, I don't do it well all the time. Okay, but yeah, do it as far as you can. Okay, so this acceleration problem, we can assume, for simplicity's sake, constant acceleration. In reality, it's never the case. Almost never the case. Assume constant acceleration. Okay, under this case, what happens? So under 0.7 meter per second, 0.7 meter per second. Okay, so after 1 second, velocity is 0.7. Okay, so every 1 second that passes, the velocity increases 0.7 meter per second. So that's the first 0.7. Okay, 2 seconds later, 1.4, and so on and so forth. Okay, so this kind of pointless to do it like that. So what is better is acceleration equals the change of velocity. Let's put the x direction again. rate of change of velocity with respect to time. This is what we call delta. Okay, delta, which is a common symbol. Okay, the small letter delta is D, or you may see this kind of D, but delta is the Greek letter. See, Greek letter used to denote change in physics. Math also, I think, but very often you at least in physics you will do that's what you will encounter. Yes, so delta is used as a Greek letter to denote change in physics. It's not a triangle or anything, it's a delta. Okay, so if we have constant acceleration, we have constant acceleration here. What's this constant acceleration? 0.7 meter per second square in the x direction. So I put delta v, well, delta v is 100 meter per second minus 0 meter per second. If this is whatever threshold it is, the time taken will be t1 or t minus 0 seconds. Yeah? So this is how you do it. You can actually use this formula to calculate the time used to get to this speed. Okay, again I will use my trusty LibreOffice. Okay, 100 over 0.7 seconds. 142 seconds. Okay, 142 seconds. Now, 142 seconds. Does that make sense? Okay, my gut feel is that 1 minute is about 60 seconds. Okay, 1 minute is 60 seconds. Now, whenever I went on commercial flights, I think those takeoff times actually took about a lot shorter than this amount. Yeah. So, but anyway, if let's just take this as the acceleration limit and let's work with it. Okay, 143 seconds. Okay. Of course, I will use more decimal places, but here we are trying to calculate how long the runway needs to be. So the runway can be longer, but it cannot be shorter. So having more time on the runway is sort of a conservative estimate, meaning to say, if the plane manages to take off before the runway ends, that's a good thing. Okay, if it takes off, if you end the runway and the plane hasn't taken off yet, then you're in trouble. So you rather have a longer runway. So we like to maybe round up the time. Okay, that's one way to think about it. Okay, so let's just do this and let's see for this 143 seconds how far you're traveling. Okay, so I'm going to put something like this. Okay, a velocity in the x direction versus time in seconds. Draw a steadily increasing velocity because the acceleration is constant. Okay, acceleration is constant, so the rate of change of velocity increase is also constant. Okay, that's the definition. Okay, right angle triangle here, you will have what's this, 100 or maybe 100 meter per second. This is 143 seconds. Okay, question is, how do you calculate distance? How to calculate distance? Okay, so for constant speed is quite straightforward. Okay, for constant speed is actually quite straightforward. Okay, so before we do the complicated case, we do the simple case first. Let's say we have constant speed. Okay, constant speed, and this is the time taken. Okay, let me call this t1. This is time in seconds. The x component of velocity in meter per second. Okay, so the distance, okay, or sx equals to vx times t. Okay, velocity of times time. Okay, maybe this is 10 meter per second. You would substitute 10 meter per second here, and then if it travels 9 seconds, then this one will okay, if let's say this is 9 seconds, 10 times 9 will give you 90 meter. Okay, that's how far you travel. But I want you to notice something. We are actually taking the area under the graph here. Okay, so that's 10 meters per second. That is the height, which is 10 meters per second. Okay, and then the length, this is the breadth. Okay, this is the length, which is delta t, yeah, the change in time, and this is the velocity magnitude. Okay, so the keynote in a velocity time graph, area under the graph, this is important, area under the graph equals the distance traveled, or displacement, yeah, displacement. Okay, so in this velocity, I'm specifically taking the x, for this case is the x component, then the area under the graph will be the displacement in the x direction. Okay, both of them must be in the same direction. Okay, so we apply this principle and we put this here. Let's find the area of this. It should be quite straightforward. Half base 143 seconds times height, 100 meter per second. And then you tell me whether this is realistic. Okay, well, you aren't here to tell me, but of course you have to check whether it's realistic. 143 times 0.5 times 100. Okay, let's see. 7150. 7150. Okay, 7150 meter. Okay, this is 7.1 km. Or maybe 7.2. Okay, so is this reasonable? Probably not. Okay, most runways are much shorter than this. Okay, but yeah, this gives you maybe a upper limit estimate of how long your runway should be at least. Okay, most runways, I don't see them going past 5 kilometers. Okay, maybe 2 to 4. Okay, 2 to 4. So maybe the allowable acceleration will have to increase. Okay, but doesn't matter. You have to, what I want you to note more is this thought process, okay, of how you use this acceleration. Okay, how did I use acceleration? Okay, I determined it using this kind of limits for the human body. Maybe instead of 0.7, we'll have 1.4 meter per second square. Okay, give it a little bit more discomfort, but you shorten your runway a lot. Okay, maybe you do that, you have a much shorter runway overall. So there are some trade-offs, you may have some discomfort and all, but the process is the same. You draw the velocity versus time graph, you calculate the area under the graph, you will get the necessary distance. So let's try with, okay, let's try with what do you call that, 1.4 meter per second square. Let's see how long this thing goes. Okay, so what I do is, again, velocity in the x direction, meter per second, time. Okay, so let's go here, 100 meter per second, and this time, what's the time taken? The time taken will likely just be half of this, because we already calculated this before. 100 over 0.7. Now 100 over 1.4 will be half of this, so that's about 72 seconds. Okay, give or take 71.5, but I'm just give or take 72. If you want to be more accurate, just take this, divide by 2. 71.42, which is about 71.5. I'm just going to use that. Okay, let's repeat the process again. If we allow more acceleration, so what's the formula? Half base, which is 71.5. Okay, this is actually the delta t, and we multiply by the velocity at the end, so 100 meter per second. So this is much shorter. So equals 0.5 times base, which is 71.5 times height, 100. Okay, this may be more reasonable, 3.575 kilometer. Okay, so again, okay, that's my bad habit. I also don't put units down there, but if you want to write the units properly, I mean, at the final answer, you must have units. Okay, so this is meter per second. This is second. Yeah, half 71.5 second. So the second and second cancel out. You get meters at the end, and then I just quickly convert to kilometers because that's easy. So this may be a slightly more palatable runway, reasonable length than let's say over here, where you have it almost 7 to 8 kilometers long, which is that reasonable? I don't think so. Yeah, this is more reasonable, but by and large, you might want it shorter because there are space constraints. Okay, runways are limited by space constraints. Okay, you need money to buy land. That's the reality. Yeah, constraints. Or you can use that land to actually do other stuff. Okay, so that's how you calculate distance, and it's always using area under the graph. Now, there is, for constant acceleration, there is a formula. There's a formula. Okay, you might see this somewhere. S equals half AT square. How did you actually get this? Okay, now for constant acceleration, the velocity, the end velocity here, which is the end velocity, Vx at whatever time you have, this is actually acceleration times time. So Vx at maybe the end time equals to acceleration times time. Okay, so if I again draw your graph here, okay, if you have constant acceleration, this will be acceleration times time. Then what's the time here? The time here is this base. Okay, this is V x equals to AT if you have constant acceleration. T is the base. Then why did this half come about? Because half base times height. Okay, so this graph will actually show you why the acceleration, okay, in if you think about it in the x direction, the displacement equals to half AT squared under constant acceleration. So do not just plug and play your formulas. S is not always equals half AT squared. Always refer back to the graph. Okay, the graph is most important. Yeah, and what I'm saying here is a velocity time graph. So that's what I want to remind you. Okay, because and this formula will not always work because in reality acceleration is not constant. Okay, maybe you have a velocity time graph, Vx meter per second, t second. Yeah, maybe you have your graph like that. So you start at 0, you take some time for your engine to start, right? And then you start increasing your velocity, and then after a while it sort of goes into some kind of this constant speed thing here. Okay, so this acceleration is not constant in most times. Not constant most of the time. Okay, so if you want to kind of calculate your runway distance, okay, same principle, area under the graph. Yeah, same principle here is area under the graph. Okay, that's how you calculate your distance traveled. Okay, displacement in the x direction. Okay, again, note the direction here. S in the x direction will be calculated from the velocity in the x direction graph. Okay, so if velocity is not constant most of the time, you will need to find other ways to find the area under the graph in order to find this as x. Now, how do you calculate like that? So, okay, so that will be for more complicated situations. For more complicated situations, okay, what we normally do is to chop up the graph. So you have a graph like this. Let's chop it up. Here's a nice rectangle. Let me calculate this. This part's easy. It's a rectangle. Okay, this part's a little bit more difficult, but it does look like a triangle, yeah? Okay, this is a curved thing, but it's not really a triangle, but it does look like a triangle. So this is a strange shape, but it maybe is like a triangle. So let me use a different color. Maybe I'll say, okay, maybe it's a triangle. I can use the half base times height formula. Okay, that will give you the rough distance. But okay, it's not really exact because over here, your areas, it will be different from the triangle. Maybe they'll cancel each other out. I mean, from the looks of this graph, it does look like it may cancel, but it may not cancel exactly. So, is there a better way? Okay. Is there a better way to calculate this kind? So, I'm going to zoom in this one. Velocity in the x direction, time. Okay, let me do it like that. So this is not going to be a triangle shape because you draw a straight line there, then this part's going to be missing. So what do you do? Okay, what do you do? Alright, so what you do is to cut it up even smaller. So let's say from here to here, okay, if your distance is short enough, this part here is almost a straight line. Okay, if your delta t, your time interval is very short. Okay, if time interval is short, okay, this is delta t, then there is less curvature. What's this curvature thingy? Okay, how curved your line is. Okay, that's what I'm trying to say. Okay, that's your curvature. But if your delta t is very small, from here to here, this thing almost is like a straight line. So that we are going to use take advantage of that. Okay, and now because this thing is a straight line, okay, I have a triangle here. I have a very small triangle, and then I have a rectangle here. Okay, I have a triangle there and a rectangle here. So the distance will be, well, there'll be this bit and this length, L2 and then L1. So the small distance traveled is equals to this small delta t and then half L1 plus L2. So this is the trapezium formula. Okay, half L1 L2 delta t. This is the trapezium formula. Okay, so alright, I have this one. Next thing I'm going to do is just cut this one up again. I'll use the trapezium formula again. I'll do the same thing. I'll calculate another delta Sx. I'll put this here. Calculate another delta Sx. Cut this here. Calculate again. Cut this here. Calculate again. Cut this here. Calculate again. Now, the thing is that as I do this and I sum, okay, sum all these small delta Sx together, okay, I get a better and better approximation as to the area under the graph. Okay, so this is the area equals the sum of all these small distances, all these small little trapezium. Okay. Now, if you really want to be so accurate and everything, you can actually make your delta t so small. Okay, this is what we call taking limits. Okay, taking limits. Okay, this is very important idea. Yeah, but I don't know whether they do it in O level, but A level definitely you will come across this. We take limits of delta t goes to 0. That means we make this time interval so small, and then we repeat this summation process so many times, okay, that you actually get the exact area under the graph. Okay, it helps you. It helps. Okay, this sum, right? This sum of velocity x times delta t sum, okay, and you limit the delta t goes to 0. All right, this whole process here is what we call integration. Okay, you might have seen this before. Integral from t equals to 0 to t equals to whatever time vx dt. Okay, so this thing here, this is a distorted s, which is a sum. Okay, so what am I saying here? Integration and differentiation is very kind of central to kinematics, but you may or may not run into the exact math of integration and differentiation. Okay, for this case, integration is important because you are calculating area under the graph. Okay, so but I just want to get you this idea that, okay, this finding of area under the graph or finding, yeah, all this is very important. Okay, so I'm not going to in this video not going to show you all the integration formula. I think that's a bit too much. This is a very long video, but I just want you to know how to calculate distance. No matter how the velocity changes or whatever, just use area under the graph. Use this is actually integration, but we don't want to say it's integration, but it's actually integration, where you just find the area under the graph using this summation process. Okay, of course, for this straight line, the summation process is kind of pointless, but I mean it will give you the same result. Okay, so if you take math and you find out about calculus, where you start learning differentiation and integration, why is it important in the real world, for engineering especially? This is the reason why. Yeah, this is one of the reasons why. In fact, Isaac Newton actually, okay, you can check me on this, check if I'm correct. Isaac Newton actually developed calculus, integration and differentiation to solve kinematic problems. Okay, and of course dynamics as well, which you talk about forces, talk about friction, all these kind of things. So yeah, do pay attention, but what I want you to take note of in all this, just remember area under the graph for distance in this velocity time. Wait, shucks, I made a mistake here. Kudos to those of you who actually saw that. Yeah, it should be time seconds, not ST, because ST looks like I'm using some displacement thingy. Yeah. Okay, let me check whether my other graphs are correct. Yeah, all of them look pretty okay. Yeah. So yeah, this let me put integration. Area under graph. Okay, this integration. Okay. I think that's it for now. I'm not going to go through that. I'll see you in the next video.